Welcome to another Senior Curriculum Inspiration, proudly sponsored by Texas Instruments Australia. My name is Peter Fox and I'll be your host and presenter for this session. The Senior Curriculum Inspiration Series is designed to help teachers develop strategies in the effective and efficient use of Texas Instruments calculators through carefully selected mathematics activities, available for free from the Texas Instruments Australia website. Today's activity is titled Vector Graphics. I'll be using the TI-Nspire CX and CX CAS. So, let's get started. In this activity, students use vectors to describe points and lines and shapes, calculate lengths, solve problems, and identify patterns. In the first part of the task, students are given 3 points. The points are on the function y equals 1 on x. We have point A located at -1, 1. Point B is located at 1/3, 3. I might check that because we might change that early on, but you'll see why and how easy it is to change. And point C is located at 4 and 1/4. So vector OA goes from the origin out to point A, vector B, and vector C. What we're going to do is enter these vectors as matrices in the notes application. You'll see why we're using the notes application as we progress through the task. Then students calculate things like vector AB, which we know is the reverse of OA plus OB. Now, whilst the calculator doesn't understand reversing the O and the A, we can use a negative sign. So, let's go into our Nspire software and see how we do all of this. I'll start, as I said, by entering a notes application, and we need to insert a maths box. The notes application can be used for text, but also for mathematical functions, equations, and so on. Now, our first vector, OA, is assigned equal to, and you'll find that we can collect the matrices command from a number of places. I'm going to use the symbols template, and I'm going to enter it as a row with -1 and -1, like so. We see the input and the corresponding output. Now, for the first question, vector OB, you'll see it's also automatically given me another maths box to work with. Now, this time, rather than entering it using the template, I'll show that you can actually enter it in manually. So if I want to enter in 1/2, comma, 2, and press enter, that has exactly the same effect. Vector OC, now I'm using assigned equals to. We could also use defined. If you're not sure where these come from, control and the symbols template gives me the assigned equals to character. I'll select it again to bring up my matrix template. You can see that it remembers where I was last time, so that's a nice efficient way to do it. And vector C, I've called 4 and 1/4. Now you recall from the brief demonstration there that we need to find out, students are asked the question, what is the vector B or AB? That's one of the early questions. So as you saw in the animation, we can put that as equal to -OA. So we'll have AB is assigned equal to -OA. You'll see the OA goes bold because it's defined, plus, now I'll demonstrate another way to pick up your variables so far. You click on the variable key and select one of your defined vectors and press enter. Now I'll demonstrate why I would use the notes application, particularly in this task where our initial points change. If I go back and change this to, let's say, 1, and to keep it on the function, 1, you can see down the bottom of the screen there that the vector AB was automatically updated. So let's just go back. I'll put my other values back in. Press Enter. Make sure you press Enter. That's the advantage of leaving that green output active so that you can be assured that the calculator has accepted your changes and not in an editing phase. All right, we come back down the bottom here, and we also, in this problem, need vector BC. So it's reasonably repetitive at the start. Oops. I just need negative OB plus OC. And of course my last one, which I'm actually calling CA, and that will be equal to negative OC plus OA. So we've got three vectors, AB, BC and CA, forming a triangle. Now, one of the early questions in it, that is question 3, we've already done questions 1 and 2. Question 3 looks at what happens if we add vector AB, BC and CA. Now, just to illustrate, I don't have to keep working on the notes application. If it's a simple question that doesn't have any further requirement, I can insert calculator application. You can use Control-I as a shortcut. You'll see that I've got access to all my vectors here. So I can do AB plus BC plus CA. And we get a 0 vector, essentially corresponding to the fact that we've got a closed figure and we started at vertex A, progressed to vertex B, then C, and then back to A. So it's a do-nothing vector. We're back to where we started from. The next thing students are asked to look at is the magnitude of the vectors. Now, because I'm going to use the magnitude calculations in a couple of different places, it's worthwhile doing them back on the notes application. Now, there's a number of ways you can work out the magnitude or the length of one of the sides of this triangle. One way, of course, is to use a magnitude command. Another one is to use a dot product. And another one is to use matrix operations. I'm going to demonstrate the easiest and most straightforward one, and that is just working out the magnitude. I'm in the notes application, so our menus look a bit different. But if I go to menu 6, that is our calculations one, that should look familiar. I'll go down to matrix and vector calculations. I don't want to create a matrix. In fact, there's a few options in there. If you weren't sure, you could go down to vector and see some of the options down there. The one we want is called norms. That works out the magnitude of our vector. So we'll take the norm of, let's say, vector AB. Now, here is where you'll find a difference between the CAS and non-CAS software. The non-CAS software will provide an approximate value there, but so far, everything else is exactly the same. So we can work out the length of any of the sides in our triangle. Now, I could also assign that to a length, as in define it like I did the other values, but you'll see it's fairly quick to get that back. So let's go down and we'll work out the length of another side. So students may choose to type these things in as well. So I'll find out the magnitude of vector BC and the magnitude of vector CA. So I've got the 3 side lengths, and then the question says, what's the perimeter of our triangle? Well, hopefully everyone can add those up, and they could, if they wanted to, use the calculator to add them up as norm A plus norm B plus norm C, but we've got a few other things that we're going to explore here. The next problem says to the students, what if we changed point A and we moved it? Now, I hope you can see that the perimeter of our triangle here is not equal to 17, and the question 5 says, where could we put our point A so that the perimeter of our triangle is equal to 17? So, probably time to put in a diagram. I'm going to put in a graph application, and I'm going to put my function in, 1 on x. I might just zoom out a little bit, move my label around, and I'll put some points on it just to illustrate or give myself a diagram of what we've got so far. I know that there's a point over here, point A, a point over here, point B, and a point over here. Now, they're not exactly where we want them, but we know that this one was 1/2, 2. We know that this one was 4 and 1/4. And this one here, I might just label them as well. That one is my point B. And this one down here is my point C. And it's my point A over here that we're about to start moving. And we want to move it such that the perimeter of our triangle is equal to 17. Well, I can draw vectors, but to save time, I'm just going to draw a triangle. So you can see how I've got options for shapes, triangle, and I'll click on my 3 points. And there I've got my triangle. Now, if I right-click, I've got the option to measure. Now, right-click on the calculator is Control and Menu. I can click on Length, and you can see that the length of my triangle, or the perimeter, is 12.6. And I need to move this so I get to 17. So I can see there's a spot over here, and I can get a reasonably good estimate of my answer. There's another spot down here. Now, here's the interesting part for this question, and we're only at question 5, is where else will I find some solutions? Now, if the students create this diagram or draw it in their books, they might see 2 of them, but they probably won't see the other 2. But let's also consider how we could help students find them. I'm going to move this, and as you can see, it creates 2 options, one down here and one down here. But I'm going to draw another triangle now. And this triangle, I'm just going to put it on these 2 points because they're not moving. And I'm going to put the other point out here, somewhere at random. I'll measure its area, its perimeter. I'll adjust it so that it's about 17. Here somewhere, it's not bad. And then what I'm going to do is change the attributes of this and lock it. Now, I have a fixed length here and 2 lengths here that can vary. Hopefully some of you will realize that creates an ellipse. To see my entire ellipse, I'll need to zoom out a little bit. And then what I'll do is I'll create a trace, a geometry trace. So we can see to expect 4 points of intersection. Now, if you're using the Nspire CAS, there's a really cool option in here. We can go back up to here. We can redefine our vector here as x, 1 on x. And what that means is all of our distances are now printed as equations. Interestingly, BC doesn't change. That's because it still uses two numerical values. So what I'm looking at doing now is solving when does norm or magnitude of vector AB plus the magnitude of vector BC plus the magnitude of vector CA. I want to know when does all of that equal 17, and I want to solve it for X. You'll see that I get 4 numerical responses, the 4 responses I was looking for. I then need to find out where they are on the function. That's not too difficult. And at the moment you're probably wondering, how do I do that on the non-CAS? The trick to doing it on the non-CAS Nspire is don't define that variable point in the notes application. Define it as a function. But it's a weird function. It is a matrix. So you simply go into your y equals editor where it's expecting to find a variable, and we're only using one variable, that is x, and then you'll find that it will also solve. The only thing that you really need to do differently, and this is all in the notes that you can download, the only thing you need to do differently is it will do a numerical solve and will only produce one value at a time. So you need to go in and restrict the domain over which it's searching for x. And our diagram that we had on page 1.2 gives us an idea that there's a point over here and a point down there. So once we've got this negative value here, perhaps go between 0 and something a little bit smaller than that negative value. And then the same on the other side, but for positive values. Now, we're just about out of time, but to give you some ideas on what else is included in this activity, I'm just going to change this back to my -1. -1. The question, or other questions in this activity, also do things like work out the area of the triangle. Now, for that one, just so happens, as the students will find, if I do a vector calculation, and we'll see here there's a couple of options for us. Oops. For example, dot product. And the notes include information about the dot product. If I find the dot product of vector AB, comma, BC, we see it's 0. How remarkable. So that tells us we have a right-angled triangle. A right-angled triangle between vectors AB and BC. After that, students are told that the point AB changes, or rather point A changes, and point B changes. We get things like 1/3 and 3. Students soon find out that they no longer have a right angle. You can see the advantage now, hopefully, of using the notes application is that everything is updating. We don't have to go back through all of those calculations again. We just scroll down. Now, for this one, students then have to do a scalar multiple of one of the vectors to extend it to a point P that creates a perpendicular line. Let me just see, because I know we're out of time. I'm going to see if I've got my old diagram here. There it is. We're just going to enlarge it a little. So the diagram you see on there heads off by the time we're up to questions 6 and 7. And we have a non-right-angled triangle. We extend side BC by some multiple out here so that we get a dot product of this line here and this line here, and students solve for that value n. They do the same again over here, and for each of the altitudes of the triangle. And in the final part where students are left to do an investigation, they find the points of intersection of the altitudes. All the instructions are there. And the really cool finish to this is that the altitudes of the triangle intersect on the line y equal 1 on x. So when they find the location, the final location of that point, and I'm going to move that over there, of this point S, in the first one, they get something like 5 and 1 over 5 or thereabouts. And then any other solution, when they try and solve it, they find the same thing, that the reciprocal of the coordinates for point S are inverse to each other, or reciprocal of each other. And students are required to make their conclusions from there. So we've got scalar multiples, dot products, perpendicular lines, areas of triangles, magnitudes, quite a lot, all bundled into the one activity. And instructions for both the TI-Nspire CX and the CX CAS. Now, we're out of time, so I'm just going to quickly check the chat space to see if I've got any questions that people want answered. I can't see any pertinent questions. There's a couple in there which I can respond to at the end of the session, as in offline. But otherwise, that's all for today. Hope you enjoyed our curriculum inspiration, and we'll see you later on in the week, hopefully, for some more. Thanks.